One of the most incredible topics we can cover in astronomy is the process of star formation. We've seen stars in the night sky all our lives, but did we ever wonder how did these stars come to be? We start with a giant molecular cloud, like the one engulfing NGC 1333 here, the Perseus molecular cloud. In the infrared range, we can actually see the molecular cloud, and in it we can see clumps of higher densities, where the material of these GMCs is more heavily concentrated. It's in regions like these that star formation takes place. And we can see many of them across the entire Perseus molecular cloud, which spans over 500 light years from one end to the other. The Perseus molecular cloud is not the only place that star formation happens, of course. Any giant molecular cloud can host this process. If we looked at the Orion constellation, again, this time focusing our attention on the pink fuzzy glow towards the bottom half of this asterism, we can see one such stellar nursery. But look at this entire region in the infrared, and you're bound to see so much more, including those hotspots of star formation. The reason these hotspots form in these giant molecular clouds is because of two of Newton's laws: his first law of motion and his law of universal gravitation, how any two objects will exert a force of gravitational attraction on one another. That's exactly what happens here between any two molecules in the GMC. The force of gravity pulls them closer and closer together, eventually causing some dense knots to form within the giant molecular cloud. As the molecular cloud begins collapsing, it doesn't necessarily collapse only on one central location. The GMC begins clumping in several regions, and these regions become more distinguishable from the surrounding free gas. It's in these clumps that we'll begin to see the first steps of star formation. The GMC happens to collapse from the inside out once the collapse has begun. It can collapse from its own weight, causing the material surrounding the core to fall inward faster. The cloud continues to collapse rapidly, with the infalling material forming what will eventually become a protostar and then a star. This collapse of a giant molecular cloud can be the result of any one of these three triggers: nearby stars going supernovae and the GMC being hit with the blast of that exploding, dying star, or from collisions with other giant molecular clouds, or from the ultraviolet radiation coming from nearby young, massive, hot stars. In the case of a supernova trigger, the expanding shell of material being blasted from that dying star can ram into the giant molecular cloud, causing the molecules to begin colliding more rapidly, and the GMC compresses inward on itself, triggering star formation. Collisions between two ISM clouds can also result in the creation of dense enough regions within the GMC to lead to star formation. Lastly, the light from young O and B type stars can ionize the surrounding gas, which can then physically move away from that star and begin compressing GMCs in the nearby interstellar medium. As quoted on the Spitzer Space Telescope's website, this animation illustrates the process of triggered star formation. First, a massive star in its final death throes explodes or goes supernova, shooting a shockwave through the surrounding clouds of gas and dust. Next, the shock wave compresses the gas and dust, gravity kicks in, and finally a new wave of stars is born. This whole progression from the death of one star to the birth of the others takes millions of years to complete. But regardless of the mechanism triggering the gravitational collapse of the giant molecular cloud, these very small, very dense clumps that begin to form within the GMC are referred to as Bok globules. Named after Dutch-American astronomer Bart Bok, these small dense clumps are the first necessary step in star formation, since these Bok globules basically serve as the cocoons for the new generations of stars to form within. Here we can see a larger view of Thackeray's globules, a set of Bok globules in Isene 2944, in the constellation Centaurus, located some 6,000 light-years away from the Earth. Although these globules may look small on this scale, each of these globules could be well over a light-year wide, the largest one possibly being two separate Bok globules overlapping each other. Within these collapsed regions of the nebula, there are competing forces at play. Gravity pulls matter more and more inwards, battling against Newton's first law, which just dictates the random motion of the clumping molecules in these cosmic dust bunnies. As it takes on more and more of that infalling material from the GMC, we start to see the Bok globules flatten out into rotating circumstellar disks with two distinct rings forming around these cores that will eventually turn into stars. The inner ring, sometimes called the protostellar disk, is the disk of material that continues falling onto the 2b star, and the outer ring is the protoplanetary disk, otherwise called a proplyd for short, which will eventually turn into planets if the conditions are right. We can see some examples of proplyds photographed in the heart of the Orion Nebula, where we are certain that new stars are forming. Even here in the Carina Nebula, not only can we see the proplyds associated with the early stages of star formation, another interesting feature of star formation can be seen when we look through this giant dust pillar in the infrared range. A jet of material is being blasted from the polar regions of the newly forming protostar at the center of the proplyd that's feeding its growth. Astronomers estimate that the material in this jet is being released sporadically from the star and traveling away from the poles at speeds around 850,000 miles per hour. Such a jet can also be seen here in Herbig-Otto object number 24. Not only can we see the very distinct jet emitted from the protostar shrouded behind the opaque dust, we can also see the bright patches of the nebula illuminated by this jet, which is a very distinguishable characteristic associated with any Herbig-Otto object. Star formation tends to happen with groups of stars forming together rather than individually. It may sometimes happen that singular isolated stars can form if their circumstellar disks are not rotating, but if they do rotate, you can see that circumstellar disks evolve into 2 or 3 stars, binary or triple systems. Examples of larger star clusters include the Pleiades cluster, which we've seen several times by now, or Westerlund 1, which is an open cluster containing 500,000 stars. In fact, one of the stars in this open cluster is so large that if we were to replace the Sun with it, it would extend out to somewhere past Jupiter's orbit. Eventually, as more and more material continue falling onto these growing cores, they get extremely massive. The dense centers begin to heat up from the increasing pressure brought on by the continuous accretion of material onto the cores. The ideal gas law dictates this phenomenon. As pressure increases, temperature increases as well to keep that equation balanced. Et voila, a protostar has formed. But a protostar is not a star yet. Rather, it's just the dense core at the center of a circumstellar disk that is contracting to eventually become a true star, but before the onset of thermonuclear fusion. These protostars are larger and cooler than main sequence stars of the same mass, and with a larger surface area, they can emit lots of energy due to the gravitational collapse that causes their formation, rather than the thermonuclear fusion that causes regular stars to emit light. Without thermonuclear fusion, no visible light is emitted from the protostar, so these protostars remain cloaked in their Bok globules, obscured from view in the visible range of light. But we can actually reveal their existence by observing them in the infrared instead. The same thing can be seen in the infrared view of the pillars of creation, where we can see countless more stars and protostars that were not visible in the original optical view of the nebula. Each of these protostars are likely surrounded by their circumstellar disks. The protostar's growing mass and increasing gravity creates the necessary pressure to raise the core temperature to 10 million Kelvin. At this temperature, thermonuclear fusion can finally begin. And with the start of thermonuclear fusion, a star is born. In this animation, the yellow, red, and white color scheme shows the density variations, not the true color, of the simulated 500 solar mass giant molecular cloud. This video takes place over a time period of 230,000 years. The process of star formation is long in the scale of our lifetimes, but relatively short compared to how long these stars live, which is ultimately dependent on their mass. With thermonuclear fusion in the star finally turned on, the star eventually reaches a state of hydrostatic equilibrium. This is a state of stability where the inward pull of the star's own gravity is balanced out by the radiation pressure pushing outward from the core. As the weight of the mass above you increases, the pressure to hold it up increases to keep balance. And this is exactly what's happening when you move closer and closer towards the center of a star. The deeper towards the core you get, the more pressure you experience from all of those overlying layers of mass. So the radiation pressure has to increase to balance that out. More massive stars have higher internal temperatures. This is a direct result of thermonuclear fusion's dependence on temperature and pressure. The rate of thermonuclear fusion increases under higher temperatures. A mere 10% increase in the temperature, say from 10 million Kelvin to 11 million Kelvin, results in the rate of helium production increasing by 46%, meaning that for every original 100 helium atoms produced, there are now 146 helium atoms being produced in the same amount of time, all because of a temperature increase of 10%. For this reason, the more massive a star is, the faster it burns out, the brighter it burns, and the younger it dies. Which brings us to the topic of stellar evolution coming up in the next unit. But first, let's take a quick detour to the HR diagram and see how these evolving protostars turned stars would appear if they were plotted on the HR diagram.